and welcome to the Spatial Structures Movers and Shakers interview series, hosted by the University of Surrey's Spatial Structures Research Centre. My name is Mark Richardson, and I'm delighted to be returning to the Movers and Shakers programme. This series was first launched ahead of the ISS Annual Symposium and Spatial Structures Conference, which was held remotely in August 2021. Over 30 world-leading academics, engineers, architects and scientists contributed their knowledge and expertise to the interviews, and it's a real pleasure to now see the series continue. Today, I'm joined by Elif Erdine, who is an architect, designer and researcher. Elif is Programme Head at the Architectural Association School of Architecture, Emergent Technologies and Design Graduate Programme. Elif's research interests include the integration of algorithmic generative design with large-scale digital fabrication tools and robotic fabrication techniques. Her wider research interests include biomimicry, complex adaptive systems, and robotic fabrication. Elif, thanks very much for taking the time to join us today.
Thank you very much for having me, Mark, and also thanks to University of Surrey Spatial Structures Research Center for having me with you today. It's very nice to be here.
Well, it's a pleasure to have you on the Movers and Shakers interview series, and also to have you as our inaugural guest of 2022, so or indeed after the conference of 2021. So thank you very much for joining us.
Thank you for having me.
Well, let's start with some introductory questions. Perhaps you could begin by giving us a brief overview of the spatial structures community in your locality, and for the benefit of our viewers, where are you based?
Yes, so I'm based in London. That's where the Architectural Association is also based, and I've been in London for the past 18 years, basically. In MTech, in Emergent Technologies and Design program, we have a very good network, interdisciplinary network between, architecture offices, engineering offices. And so in terms of, let's say, spatial structures community, we work very much with offices such as Apple Engineering. We've had collaborations in the past with AKT, Arab. So it's a kind of a very wide network, and that network is both fed, let's say, by our relations with them, but also by the alumni who finish MTech, because, for those of you who might not know, MTech is an interdisciplinary program. So we have students both from engineering background and architecture background. And so that kind of also keeps our relations fresh with the existing community in London.
That makes sense. Thanks, Elif. And we touched on your background by way of introduction, but maybe you could give us a more of an overview of your career journey to date.
Sure. I mean, I completed my Bachelor of Architecture in Istanbul Technical University, and 18 years ago, I moved to London to pursue my master's degree at the AA, Architectural Association. And after that, I worked for several years for Zaha Hadid Architects. I took part mainly in competition projects, And during my time at Zaha Hadid, I came across Michael Weinstock, who is the founder of Emergent Technologies and Design. I came across his writings on nature, learning from nature, biomimicry, complexity, emergence in nature, and how those principles in nature could be translated into architecture. So that kind of started a new interest in me, and I really wanted to pursue a PhD. And so I started my PhD at the A in 2010, and which was completed in 2015. And I also started my teaching journey at the AA when I started my PhD. First, I started with several workshops. So AA has this visiting school network, which are a series of short courses around the world. So I started with those, and I started exploring digital fabrication, robotic fabrication, and integration with computational systems. And then I started teaching in MTech, and for the past 3 years, I'm the program head of the MTech program, basically.
Brilliant.
So it's been an ongoing journey.
Absolutely. Thanks, Elif. And could you tell us about a research paper or project you are currently working on?
Yes, so we are currently working on a research paper, which actually I'm going to talk about the project shortly. So it's a pavilion that we built last year on Bedford Square in collaboration with Hassel Studio and Bureau Heppel Engineering and One Click LCA, which, as I said, I'm going to describe shortly. It's really about upcycling timber and how it's about sustainability, upcycling timber and how basically we can build, let's say, load-bearing structures with upcycled materials. And I will be talking about that in a bit.
Fantastic. Well, that leads very nicely on to our middle section of our interview, which is entitled Your Space, Your Structure. So at this point, I hand over presentation rights to Elif, who will be presenting for a short period of time on a spatial structures topic of interest to her. So without further ado, over to you, Elif.
Just to give a bit of, first of all, brief overview before I talk about the projects that I'd like to discuss with you today. As I said, I'm the program head of Emergent Technologies and Design postgraduate program at the AA. And the way we approach emerging technologies are really, the intention is to address emerging problems in the world. And obviously, today I will be talking mainly about structures, but we actually work across multiple scales. So we work on architectural solutions, ecological solutions, urban solutions, material systems. And for all of these systems, we work with various design methodologies. These design methodologies can be obviously computational-based, simulation-based, and they can even be software applications. So just to give a brief overview of the kind of research on spatial structures that have been undertaken in MTech for the past 20 years. This is a video that shows very quickly, as I said, an overview of what we have been developing in MTech. So for the past 20 years, we've been experimenting with novel design processes, computational methodologies, building systems. And I just want to stress here that all of our computational experiments are really calibrated from physical experimentation. So we really first look into material behavior on a, let's say, component or regional scale, and then we're interested in quantifying these material behaviors to develop more complex computational systems. We believe that it is impossible to build your knowledge from only one project. So we try, let's say, not to use more than one technique or one methodology in one project. And we like to approach research as a craft tradition, basically, as an atelier tradition. So rather than developing, let's say, one big tool, we believe that it is more intelligent to design smaller tools tailored for every individual project. You're seeing also at the same time some of the workshops that we have been conducting throughout the world, Istanbul, London as well as the research that we're undertaking in MTech. Our approach is very much inspired by nature, but, and I'm sure you've heard this phrase, form follows nature, but what we're really talking about here is not imitating the forms of nature. This is something that has been done a lot in the past, but we're really talking about designing using the processes of nature. And that's really the evolutionary process that I would like to talk about today. Understanding evolutionary processes and principles. So if we kind of, let's say, approach biological principles, biology, design, and computation as three different fields, we believe that we can create a bridge between evolutionary principles and design through computation, through computational processes. And this bridge can create a feedback loop where design and computation influence one another. As we might all be very aware, architecture has a kind of a, let's say, multifaceted nature across different scales. And the majority of the problems that we deal with in architecture deal with multiple different objectives. And that's why evolutionary computation and in general, learning from nature is very relevant, because obviously nature teaches us about complex systems that emerge from the, let's say, local interaction of parts. And this understanding, or this way of approaching architecture, is a field where we're dealing with multiple conflicting objectives, really necessitates us to question the architect's role. When, as architects, we use these methods, or let's say learning from nature, when we look at nature, understanding evolutionary principles, when we use this as a method of solving a problem, our role will essentially change from coming up with a single solution to coming up with a series of questions and a series of architectural problems. And that's how we approach our design problems across various scales in MTech. So for us, it's really about designing the architectural question or the problematic, and not coming up with a singular solution. So if we set this kind of approach on one side, I want to kind of give you a brief summary before I jump into the project of the kinds of constructions, spatial structures that we have been building in MTech for the past 2 decades. And the kind of emphasis for today will be timber structures. And so at the AA, in MTech in particular, we're interested in the culture of making. We really enjoy making, and we collaborate with engineers as well, and we really believe in learning by doing, basically. And over the let's say 2 decades, we've built several structures made with timber that have obviously different functionalities, that are created with let's say lightweight timber panels or sheets, and through the employment of different techniques, such as different types of formwork or ways of creating curvature, inducing curvature in different directions, we have been designing these self-standing structures. In most of these structures, we have collaborated with Bureau Heppold Engineering. This one that you see was a collaboration with ETH. Another example is study based on creating, let's say, a doubly curved self-standing structure based on the different material behavior, or let's say the material behavior of timber in different directions. Some examples of that: this was a collaboration with Arab. And as I said earlier, in each of these structures, we have been exploring a specific technique that can be geared towards, let's say, inducing curvature or joinery, or a combination of both. And these projects are very much student-led. They begin with tabletop models, as you see here. And then they, through obviously iterative experimentation, physical experimentation, its translation to computational systems, they are scaled up to, let's say, regional scale experiments. These are our MTech students that you see, and after which they're scaled up to one-to-one scale load-bearing structures. And I particularly like this image because it really shows, the kind of interaction between the computational paradigm, where our computational models embed a lot of data, data relating to how, let's say, components can be aggregated, assembly sequences, so on and so forth, and the actual build structure. So the structure that I would like to discuss with you today was a collaboration between MTech and Hassel Studio. For those of you who might not be aware, Hassel Studio is a very large architectural office based in Australia. They also have offices in London, New York, Shanghai. So we were approached by Hassel basically for this collaboration. This pavilion, the Remerge Pavilion, we built this last year, around a year ago, actually, almost exactly a year ago. It was open to the public on Bedford Square for a month. Our structural consultants were Bureau Heppold Engineering, and our life cycle assessment consultants were One Click LCA. And so this is Bedford Square, where the AA is located. It was a really, in terms of timing, it was quite nice actually, because this was right after we moved back to our studios. You know, after lockdown, we were online for a year or so. And so when Hassel approached us, it was right around the time that we were back at the AA. So it was a really nice way to, you know, come back to our buildings and, you know, kind of restart that making culture again. So I will first describe the design principles for the pavilion. So Hassel Studio asked us basically to keep the carbon footprint of the project to an absolute minimum. And so they asked us to use only reclaimed wood for this pavilion. Of course, using reclaimed wood panels or planks requires us, or it requires the system to be modular. And it was also a good opportunity for us to examine life cycle assessment methods and to think about how we could include them from the early phases of design. So obviously modular, the advantages of a modular system is that, you know, we're really looking into a streamlined fabrication process, streamlined assembly and disassembly process. So, you know, not only we are exploring the second life cycle of the timber planks, but being modular, we can also think about the third life cycle of these planks as well. And the system also facilitates addition or subtraction. And as I said earlier, recycled timber enables us to rethink about the carbon footprint and the ecological impact of using this material from the early phases of design. And throughout our research, we actually realized that recycled timber planks are the most abundant, let's say, timber elements in the AEC industry. And so this kind of shared understanding, let's say, of how construction waste can be useful as a research, let's say, methodology, led us to redesign using these timber planks for a lightweight outdoor structure and to highlight the ecological impact of the project from the early phases of the design process. So we all know that wood is by nature the best biodegradable material, right? It is renewable, resilient, long-lasting. And when a wooden building is demolished after a few decades, it doesn't produce, let's say, useless waste, but instead produces reclaimed wood that can be reused in other building applications after dismantling. So the first thing that we did was to go around London to timber recycling facilities to collect basically as many timber planks as we could. These are the kind of general, let's say, the kind of average available length, width, and thickness of wood planks that we found. And I say average here because actually, obviously, these were not standardized sizes. Each of the planks had some kind of small variation in the width and thickness, which I will touch upon later because it obviously creates a challenge in the computational process. So we started thinking about how we can create, let's say, as lightweight a structure as we could with timber planks. And initially we thought about curve banding, so introducing scores into the timber planks, and these can be parallel or radial scores. And we also were careful about the joiner system. So we didn't want to, or we wanted to minimize the kind of secondary materials in the joiner system. So that's why we started exploring cross-slab joints and how we could join these planks after that to create a regional scale aggregation. So this shows the kind of system principles. We have these timber planks, which are scored and also steam bent. So it's a combination of two techniques, creating 100-degree angles within one plank, and then joining these planks to let's say, create this rib system. And this RIP system is then rotated and aggregated to create a self-standing structure. So this was the, let's say, initial conceptual design idea that we had. This design we also submitted for Tele Architecture Biennale last year, and we were a finalist in that competition at the same time as we were developing the pavilion itself. So these are the initial timber planks that we collected, scoring process. And during this stage, our students did a lot of physical experiments with the material that we found. So how much it can be bent, how much distance between each score, how deep should the scores be so that the material that actually doesn't break, as well as recording the production time of each experiment to estimate how long the final production phase would take. And of course, recording the springback values as well. So it was quite an iterative process. This was during the summer of 2021. And of course, documenting and recording all of these experiments. And as I mentioned earlier, using life cycle assessment was quite important in this phase. So using LCA as a design driver in the computational workflow basically allowed us to consider not only the material itself, but also the carbon emissions associated with its origins and transportation to Bedford Square. So that accounts for A1 to A5 stages, basically. So the material itself is transportation and the construction phase. And in initial analysis of most types of plywood used for exterior construction versus, let's say, solid wood planks shows that plywood's carbon emissions are significantly higher in preparation than solid wood planks. So that's why, again, this kind of solidifies the fact that using solid wood planks is beneficial. And at the same time, the same effect of reducing carbon emissions occurs when we compare newly produced solid wood versus reclaimed wood planks. So we got this kind of initial understanding and data from LCA, and obviously initial, let's say, finite element analyses of the structure was also quantified. And all of this data, so, you know, the physical experimentation, the life cycle assessment, and the structural analyses, all of this was integrated into a multi-objective optimization workflow, which in this case, we use WALL-E, which is an evolutionary solver for Rhino Grasshopper 3D, has been developed by MTech PhD researchers, basically. And so, you know, in this collaboration between architecture and computation, through the employment of this method, there are three important steps. One is the design problem, initial step, evolutionary algorithm, and the selected solutions. And of course, you know, the computer does the kind of evolutionary algorithm part. So it's really, again, going back to my previous point about, as architects, you know, we need to design the problem itself, and we need to analyze the solutions and select the appropriate ones. So this is a simulation that basically shows all of the information that was translated from the physical experiments to a computational system where we're looking into variation within one, let's say, RIP system. And in the next phase was to create a morphology from all these RIPs while simultaneously measuring the carbon footprint as well as the structural behavior. Sorry, one of these videos is not playing. So we can create, let's say, thousands of solutions. But of course, the important part here is to analyze how they perform. And, you know, everything is numerical, everything is data-based. And so from these solutions, we selected one solution that was appropriate for further development within the time frame that we had. And of course, our computational model embeds all of the data in terms of, let's say, construction assembly sequences as well. These are, as I said, some of the initial experiments, initial ribs coming up last summer, joiner details. This was important for us because, as I said earlier, we didn't work with standardized sizes, but the thickness and the widths were varying a lot, and we had to embed that in the computational system, keeping track of, at the same time, what was broken, how we could replace it, and how we could update the computational system simultaneously. And at the same time, our students developed an AR app, and I will jump into the relevant part here, where we could actually use the app to project the structure itself, which helped quite a lot with our assembly process. This is showing the assembly process by our students. It took around 5 days. Oops, sorry. And some final images. And here I just want to kind of conclude by emphasizing that, we like to capture our structures through, 3D scanning. That's very important for us because afterwards we can overlay this information, the 3D scan information, with the final digital file to understand how the actual structure worked. You can see some of the deflections here in the cantilever area, for example. And this is important for us to basically, obviously afterwards, to write about when we are writing a research paper. We can use this information to throw out conclusions and observations on how, in the next iteration, the structural system can be improved. And the disassembly process, this is showing the disassembly process. So basically, we gave most of the timber planks back to the recycling facilities. Some of them are kept in MTech Studio, some are in Hassel Studio. So they're still kind of continuing, let's say, their third life cycle. And for this collaboration with the Hassel Studio, we won the Architizer A+ award in architecture and collaboration. And I just want to finish by kind of emphasizing the importance of collaboration between academia and industry partners, structural consultancies, or any kind of, let's say, software consultancies, because that creates obviously an information loop, a feedback loop, which we believe then leads to innovative workflows and research outputs. And thank you.
Elif, thanks very much for taking us through your presentation there. Really interesting overview of your work across a number of projects, but particularly with respect to timber, which is very handy in terms of our end section of questions, which looks at the question of sustainability and spatial structures. So could you tell us, what are your personal views with respect to the question of sustainability and spatial structure projects? How can sustainability be improved within our community and its outputs?
Yes, thank you for the question, Mark. Well, I mean, as I tried to explain in the presentation, we're not like we're interested in approaching the question of sustainability from the early phases of design, and that's why quantification of data is very important. And now, we do have the computational tools to tackle this issue, like is in the case, for example, we use one-click LCA, which was quite helpful. This was the first time we used one-click LCA, and in general, including life cycle assessment into the design process. But I do think that, as a general practice, it's important for architects and engineers to consider, embodied carbon and issues related to carbon emissions, starting from the material through to transportation, construction phases, to include these parameters in the early phases of design, rather than approaching it, let's say, at the later stages of design, because at that point, it's not really helpful. So that's kind of my overall view, and this is something that, you know, we're investigating in MTech as well. You know, that is, and the project that you saw was the kind of first case study into that.
No, that makes sense, and it was actually really interesting to see in your presentation the efforts you'd gone, quite rigorous efforts to quantify
Yes.
the impact of carbon. So yeah, very pertinent. Thank you. And what examples of sustainability best practice have you seen on recent spatial structure projects? Whether that's a project you worked on or another project.
Well, I mean, you know, rather than talking about my project, because I've already discussed it. So I think, you know, rather than giving one or two projects, let's say, names, I think that for me, and you know, in relation to our research in MTech, it's important to explore local materials, you know, rather than importing materials from 1,000 kilometers away. We believe that it's important to utilize locally sourced materials. And this is something that in part, as part of our kind of larger research domain in MTech, you know, I talked about ecological solutions, urban solutions, right? So what our students investigate in MTech are really exploring, let's say, local biomes where there are pressing issues, you know, that might be related to climate change, obviously, let's say sea level rise, migration, like of various populations, so on and so forth, and understanding the local context and what can be built that that can adapt well to that environment using the local resources. So I really think that we should emphasize the use of local resources. And in, you know, when doing that, of course, there are a lot of things we can learn from traditional crafts, right, that have been developing in those biomes for perhaps centuries, but exploring how they can be enhanced, developed further by using, let's say, these new novel technologies and techniques that we have in our hands as designers and engineers.
Absolutely, no, great answer. Thanks, Elif. Thank you for that. Well, we've actually amazingly reached the end of our interview. It's been a a real joy to speak to you today and to learn about your research and some of the really exciting projects that you've been working on throughout your career, but also in the recent years of the last couple of years that you were kind enough to cover. For those watching the series, if you've enjoyed this video or indeed any in the Movers and Shakers series, please do remember to like, share and comment. All of your views and thoughts are welcome. And do follow Spatial Structures on LinkedIn, Facebook, Instagram, Twitter and Bilibili. Details of our social channels can be found in the description section below. So that just leaves me to thank Elif for joining us today and for, as I said, being our first guest in our slightly revamped Movers and Shakers interview series. It was a real joy to speak to you, and hopefully we'll get the opportunity to catch up with you again very soon.
Thank you so much. Thank you for having me. I look forward to that too. Thank you, Mark.